The topic of this chapter is thermodynamic equilibria. We will talk about phases, phase equilibria and chemical equilibria. A phase is a region of space, throughout which all the macroscopic physical properties are continuous. In other words, a phase is a continuous thermodynamic system. The interface between two phases is a phase boundary. Some of the macroscopic physical properties are discontinuous across a phase boundary. In the following example, liquid water is a phase. Temperature, density, and all other physical quantities are continuous in the liquid phase. Solid ice is another phase. Temperature, density, and all other physical quantities are continuous in the solid phase. The interface between liquid water and solid ice is a phase boundary. The two phases can have same temperature. However, liquid water and solid ice have different densities. Therefore, the density is discontinuous across the phase boundary. Pay attention to the difference between the terms phase and state of matter. The state of matter refers to the interaction strength and distance between particles in a macroscopic system. The state functions of a state of matter are not necessarily continuous. In other words, in one state of matter, there may be more than one phases. For example, a system with liquid water and liquid oil has only one liquid state. However, liquid water and liquid oil have different densities. The density is discontinuous at their boundary. So, there are two liquid phases in this one liquid state. The phase transition is the change of a system from one phase to another phase. Typical phase transitions are the transitions between states of matters. Please try to remember the terminologies of the phase transitions between solid, liquid, gas, and plasma phases. There are also phase transitions within a state of matter. For example, beta tin, white tin, transits to alpha tin, gray tin, below 13.2 degrees Celsius. Both white tin and gray tin are in solid state. White tin is a metal with body-centered tetragonal lattice. Gray tin is a nonmetal with a crystal structure identical to diamond, FCC. White tin and gray tin are two allotropes of tin. The transition from white tin to gray tin is also known as tin pest or tin disease because it destroys the metallic properties such as ductility and malleability, which deteriorates tin objects. If two or more phases are in thermodynamic equilibrium, there is a phase equilibrium between them. For example, liquid and gaseous bromine are in phase equilibrium at about 298 Kelvin and 0.715 bar. In another example, at 273.16 Kelvin and 611.73 Pascal, solid ice, liquid water and gaseous water vapor are in phase equilibrium. From here, all the systems discussed are in internal equilibrium. That is, all the physical quantities are identical in each phase. A phase diagram is a chart to show phases occurrence under different conditions. The phase diagram of a single component system is a two-dimensional chart with temperature and pressure as variables. Each phase occupies an area in the phase diagram. A curve between two areas is a line of equilibrium where the two phases coexist. It is also called a phase boundary. Some macroscopic properties are discontinuous across a phase boundary, such as the density. The intersection of phase boundaries is the condition under which three or more phases coexist in phase equilibrium. If three phases coexist in phase equilibrium, the intersection is called a triple point. There is also a critical point on the gas-liquid phase boundary. No phase transition exists at higher temperature and pressure than the critical point. The phase with higher temperature and pressure than the critical point is called supercritical fluid. It has many unique properties and applications, but we will not discuss it in general chemistry. The phase below the gas-liquid and gas-solid phase boundaries is also called vapor. A vapor can be condensed to liquid or deposited to solid by increasing the pressure on it, without reducing the temperature. The degree of freedom of a system is the number of state functions, which can change independently from each other. The Gibbs phase law states that the degree of freedom of a system depends on the number of components and the number of phases in equilibrium. The Gibbs phase law can be understood in the following way. We start with a pure ideal gas. The ideal gas law tells us, if the pressure and temperature are free to change independently, the volume is determined by the pressure and temperature. Furthermore, according to the knowledge we learned from previous chapters, all the other state functions, such as internal energy, enthalpy, entropy and Gibbs free energy, are also determined by pressure and temperature. So, the degree of freedom is 2. If one more component is added to the system, the degree of freedom increases by 1. The fraction of the added component is another state function that can change independently from pressure and temperature. If C components exist in the system, the degree of freedom increases by C-1. The additional free state functions are the fractions of C-1 components. If 2 phases are in phase equilibrium, the degree of freedom decreases by 1. It is because the equilibrium exerts one more relationship to the state functions. If p phases are in phase equilibrium, the degree of freedom decreases by p-1. It is because p-1 relationships are exerted to the state functions due to p-1 pairs of phase equilibrium. Let's use the phase diagram of water as an example. There is only one component, water. So, C is equal to 1. Within each area, there is one phase. So, P is equal to 1. Thus, the degree of freedom is 2. The temperature and pressure are free to change independently. At a phase boundary, 2 phases are in equilibrium. So, P is equal to 2, and the degree of freedom is 1. The pressure and temperature are dependent on each other. Only one of them is free to change. When 3 phases are in equilibrium, at the triple point, P is equal to 3, and the degree of freedom is 0. All the state functions are fixed. At the triple point of water, the temperature is 273.16 Kelvin. Pay attention, it is not 0 degrees Celsius but about 0.01 degrees Celsius. The pressure is 611.73 pascals. By the way, you can see that the solid-state ice has many different phases. For a 2-component system, also known as a binary mixture, Gibbs phase law tells us that the degree of freedom is 3 in a single phase. Thus, a complete phase diagram of a binary mixture is a 3-dimensional graph, which is difficult to present in a 2-dimensional paper. Thus, the phase diagram of a binary mixture is usually given at a certain pressure, for example, standard pressure. As such, the phase diagram reduces to 2-dimensional, with composition and temperature as variables. Such phase diagram is called a CT diagram. Here, I show you a typical CT diagram of AB system, with 2 solid phases, alpha and beta, and 1 liquid phase, L. In a CT diagram, an area is either a single phase such as L or alpha, or mixture of 2 phases, such as alpha plus beta and L plus alpha. At a 2-phased area, composition of each phase is determined by the temperature and pressure. The degree of freedom is 2. At the phase boundary where 3 phases coexist in equilibrium, both temperature and composition are determined by pressure. The degree of freedom is 1. For example, the iron carbide phase diagram is one of the most famous and useful binary phase diagrams. The percentage of carbon present and the temperature define the phase of the iron-carbon alloy, and therefore, its physical characteristics and mechanical properties. The percentage of carbon determines the type of the ferrous alloy, iron, steel or cast iron. In the iron-carbon alloys, alpha ferrite and austenite, gamma iron, are BCC and FCC iron allotropes with dissolved carbon atoms respectively. Cementite is iron carbide. They are single-phased. Pearlite is a layered structure composed of alternating layers of alpha ferrite and cementite. Ladeburite is a mixture of austenite and cementite. Pearlite and ladeburite are 2-phased.